Traditional gyroscopes rely on a simple physical principle. A massive, continuously spinning wheel will conserve its angular momentum and maintain its orientation in space, regardless of how its housing moves. This mechanical rigidity provided highly accurate navigation for decades. It steered maritime vessels across oceans and stabilized massive aerospace platforms like the Hubble Space Telescope in orbit. But modern embedded systems and portable electronics present a strict physical boundary. You cannot install a continuously spinning, three-dimensional mechanical rotor inside a microscopic flat silicon chip. When engineers scale structures down to the micrometer level, the physics change. Microscopic mechanical parts lack the mass to maintain momentum, and they are highly susceptible to overwhelming stochastic noise and bias drift, random, unpredictable errors that accumulate over time.
To extract navigational precision from a non-spinning piece of silicon, engineers had to completely abandon classical rotational mechanics and find a new physical paradigm. The solution is the Micro-Electro-Mechanical System, or MEMS gyroscope. Instead of relying on a spinning mass, these sensors measure angular rate by exploiting a physics loophole known as the Coriolis effect. The Coriolis effect dictates that if a mass moves in a straight line, with any frame of reference that begins to rotate, that mass will experience an apparent force perpendicular to its direction of travel. Because a silicon chip cannot spin 360 degrees internally, engineers use a flat, vibrating structure to simulate that required motion. By driving a microscopic mass rapidly back and forth along a single axis, the system creates the continuous linear velocity vector needed to trigger the Coriolis effect. When the external device, and therefore the entire chip, rotates, the internal vibrating mass is forced to displace orthogonally, or at a right angle, to its driven path. Replacing a spinning rotor with a vibrating plane solves the physical packaging problem, but it simultaneously introduces a massive signal processing challenge, accurately reading a displacement that is often smaller than the width of an atom. To understand how this works, we start with a baseline mathematical model, a stationary inertial coordinate system labeled OXYZ, containing a secondary reference frame, O', X', Y', Z', spinning around the z-axis. Inside that rotating frame, a singular particle, point M, traces out its absolute velocity vector. By taking the first derivative of that velocity vector with respect to time, we find the absolute acceleration of point M. The math breaks this down into three distinct components: relative, implicated, and Coriolis acceleration. We only care about the Coriolis component. This specific acceleration is the mathematical cross product between the rotational angular velocity of the frame and the relative velocity of the moving particle. A key rule of the cross product is direction. The resulting Coriolis acceleration vector is strictly perpendicular to both the particle's travel path and the axis of rotation. This gives us a highly useful physical relationship. If the system strictly controls the relative velocity of the mass, any perpendicular acceleration it measures is a direct proportional indicator of the external angular rotation. Engineers translate that kinematic cross product into hardware using a 2-degree of freedom mass spring damper system, a flat, rigid mass suspended by elastic support beams in a strict plane. In drive mode, an electrostatic module forces this mass to rapidly oscillate exclusively along the horizontal x-axis. This constant motion along the x-axis satisfies the first half of our equation. It provides the known, tightly controlled relative velocity that the math demands. When an external angular rate is applied around the z-axis, meaning the device physically turns in the real world, the Coriolis force causes that oscillating mass to deflect slightly along the y-axis. This y-axis deflection is the sensor's sense mode. It is the physical, measurable manifestation of the Coriolis force. Microscopic capacitive plates are positioned along the y-axis. As the mass moves closer to or further from these plates, it changes the local electrical capacitance, converting that mechanical displacement into a fluctuating voltage. By mechanically isolating the axes, driving motion in the x-axis, specifically to sense tiny displacements in the y-axis, a microscopic solid-state chip can successfully detect three-dimensional rotation. But reading these microscopic capacitive changes presents a severe vulnerability. The signals are so faint that they are easily corrupted by stochastic processes. Minor environmental factors, like temperature fluctuations and physical vibrations, create chaotic, overlapping errors that rapidly degrade the accuracy of the angular velocity data. Traditionally, engineers analyze sensor noise using power spectral density, or PSD. PSD is an analysis method that converts time series data into the frequency domain. However, PSD carries a high computational cost that strains low-power embedded systems. To solve this, engineers use Allan Variance. Allan Variance is a time domain analysis method that requires far less computational power to analyze inertial drift. The core mathematical principle of Allan Variance involves taking a long, continuous stream of noisy data and slicing it into distinct time bins or clusters of varying lengths. The algorithm then calculates the mathematical average of each bin and compares the variance between them. Grouping data points into these specific durations separates overlapping noise sources based on how they behave over different timescales. Allan Variance acts as the diagnostic bridge between noisy physical hardware and reliable digital data. It allows engineers to isolate, identify, and quantify specific flaws in the sensor's performance. This chart shows an Allan Variance log-log plot mapping Allan deviation against averaging time. Because stochastic noise sources are statistically independent, they appear as distinct asymptotic slopes. The line dropping at a negative 0.5 slope represents angle random walk, or ARW. ARW dominates the signal at short averaging times. It is the high-frequency variation that appears as standard rapid static in the sensor's immediate output. As the averaging time increases, the line flattens out horizontally to a slope of 0. This indicates bias instability, a low-frequency noise that emerges over slightly longer durations. This flat bottom is a critical metric. It represents the sensor's absolute performance floor, defining the best possible baseline stability the hardware can mathematically achieve. Moving right, the line climbs at a positive 0.5 slope, representing rate random walk, a long-term drift where the baseline offset changes permanently. Finally, it steepens to a positive 1 slope, marking the drift rate ramp, a slow, compounding monotonic error. By isolating these exact slopes, engineers extract the specific mathematical coefficients required to write active error correction algorithms for the host device. Executing these corrections introduces a final challenge. Continuously reading noisy voltages and calculating calibrations keeps the host microcontroller active, draining massive amounts of battery power. Modern integrated circuit architecture solves this with hardware sensor hubs and FIFO buffers built directly into the MEMS module itself. The sensor hub collects and buffers raw data from the primary gyro locally, bypassing the main processor so it remains inactive. The sensor hub can also simultaneously ingest data from external sensors, like magnetometers or accelerometers, and perfectly align their timestamps with the gyroscope data in the buffer. The final digital layer is the Intelligent Sensor Processing Unit, or ISPU. It acts as a local processor, performing low-power sensor fusion and applying noise correction algorithms directly on the edge. Offloading this high-frequency data buffering and filtering allows the host microcontroller to remain in a deep sleep state, drastically reducing overall system power consumption. By mastering the kinematics of the Coriolis effect, mapping stochastic limits with Allan Variance, and leveraging edge-buffered architectures, engineers have successfully extracted macro-scale navigation precision from microscopic silicon.